NASA spotted something new on interstellar comet 3I/Atlas today, and honestly, this thing just won't quit. Here's how it's supposed to work. A comet swings past the sun, puts on a show with some wild flares, then slowly dims as it heads back out into deep space. Pretty straightforward, right? Except today's data tells a completely different story. 3I/Atlas is still going. If you've been keeping up with this and want to know what happens when an interstellar visitor refuses to follow the rules, stick around. What NASA's seeing right now might be the clearest evidence yet that this object isn't winding down at all. It's still in the middle of something. So, what exactly did they find? Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. The observation session started normally enough. Fresh images came in, brightness readings were taken, position data logged from multiple observatories around the world. On paper, everyone expected something pretty mundane, just another small dip in brightness as 3I/Atlas drifts farther from the sun and slowly fades away. Then they looked at the first plot, and that plan fell apart immediately. When they overlaid today's brightness measurements against the predicted decline, the curve didn't drop like it should have. It flattened out instead. In some wavelengths, it actually ticked upward a bit. This isn't some massive explosion or dramatic outburst. It's something more subtle and, frankly, more concerning. The comet is staying brighter than it has any right to be at this distance from the sun. Given how much sunlight it's receiving now, it's producing way too much light on its own. That's your first clue that something fresh is happening. If this were just old dust drifting away on momentum alone, the glow around the nucleus would look soft and diffuse by now, like embers cooling down. But when the team stacked today's deep exposure images, that's not what they found at all. The inner region around the nucleus is still crisp and sharp. Right at the core, there's a tight, bright center with a new faint arc wrapped around it. It's a thin shell of material that wasn't visible in previous image stacks. Think of it like a fresh ring expanding outward, the signature of a recent burst that happened recently enough that we can still see its leading edge pushing through the coma. Farther out, the main tail still has that well-defined spine running down its center. There's a narrow, bright lane where dust particles are being funneled into one dominant direction by the comet's activity. On top of that, today's images reveal a small fan of material peeling off at a slightly different angle. That's probably a side jet that either just turned back on or got significantly stronger. None of that geometry screams dying comet. It screams still actively outgassing. Then there's the rotation issue. NASA's observation teams track tiny brightness variations over several hours to figure out how fast 3I/Atlas is spinning and which parts of its surface are actively venting material. The process is pretty straightforward. You take the brightness measurements over time, fold them over the previously calculated rotation period, and check if all the peaks and valleys line up consistently. Today, they didn't line up. The main brightness peak showed up earlier than the last rotation period would have predicted. There's also a secondary bump in the light curve that used to be weak and irregular. Now it's sharpened into a clear, repeating feature that appears at the same point in every rotation cycle. To make the new data fit, they had to adjust the rotation period again, shaving off a tiny bit more time. That means the nucleus has spun up slightly faster. And the fact that this secondary bump is now stable and predictable tells you something important. There's a second active region on the surface that's firing regularly now, not just sputtering on and off randomly. So, let's take stock of what we're seeing. A brightness curve that's refusing to drop the way models predicted it would, a new inner shell structure in the coma from a very recent pulse of activity, a stable secondary active region showing up consistently in every rotation cycle. That alone would count as fresh activity. But there's one more piece of evidence NASA can't ignore, and it has to do with the comet's trajectory. Every time new position measurements come in from observatories, the team reruns the orbital calculations. They're essentially asking, how much extra acceleration from jets do we need to account for to explain where this object actually is right now? If the comet were finally settling down, those non-gravitational acceleration terms in the equations would be getting smaller and smaller. The orbit would start looking more and more like the clean path of an inert rock responding only to the sun's gravity. In today's orbital solution, that didn't happen. The tiny rocket-like force from outgassing jets is still required to make the math work. The strength of that force hasn't dropped close to zero, and its direction has shifted slightly again, which lines up perfectly with the new asymmetry in the inner coma and that little side fan visible in the tail. So, the orbital mechanics, the images, and the rotation data all point to the same conclusion. NASA didn't just catch leftover glow from past activity today. They identified ongoing, fresh activity happening right now. So, what's actually driving this behavior deep inside the comet? The best working explanation is that we're witnessing a delayed chain reaction from its close encounter with the sun. Some weeks ago, when 3I/Atlas made its dive through the inner solar system, the outer layers responded first. The soft ices near the surface started sublimating immediately. Loose dust got swept away, shallow fractures opened up. Those surface reactions gave us the spectacular early activity everyone was watching. But the heat that started back then is still propagating inward through the nucleus. The inside of a comet isn't some uniform block of ice. It's more like a messy conglomerate of different materials. You've got pockets of volatile ices embedded in rock and dust, ancient rubble compacted together over millions of years, veins of material packed along old fractures from its time drifting through interstellar space. Each of these pockets has its own unique breaking point, its own temperature threshold, where it finally gives way. And here's the thing, those pockets don't care that the comet is heading back out into deep space now. They don't respond to how far the comet is from the sun at this moment. They only respond to the temperature right where they are, deep inside the nucleus. Once the slowly advancing heat front finally reaches one of those deeper pockets and pushes it past its threshold temperature, it vents explosively. When one of those buried pockets lets go, three specific things happen. First, fresh gas and dust come rushing out into the coma. That creates new expanding shells around the nucleus and keeps the overall brightness higher than surface models would predict. Second, the direction of the outgassing shifts depending on where that pocket is located on the nucleus. That shows up as a new fan in the tail, pointing in a slightly different direction and produces a measurable change in the non-gravitational push on the orbit. Third, if that jet is firing from an off-center location, it applies torque to the nucleus that spins it up and changes the pattern you see in the rotation light curve. From our perspective, watching from Earth, all of this looks like 3I/Atlas refusing to die out like a normal comet should. But from the comet's internal perspective, it's still processing and releasing the enormous amount of energy it absorbed during a single brutal pass near our star. And here's the worrying part. This latest stage activity isn't free. It comes with a cost. Every late-firing jet adds mechanical stress through torque. Every adjustment to the spin rate changes how centrifugal forces pull on regions that might already be cracked or damaged from earlier outbursts. Every new fracture that opens up to vent gas also weakens the structural integrity holding the entire nucleus together. We've seen this exact pattern play out with comets from our own solar system. The ones that stay active deep into their outbound journey, showing evolving rotation states and changing coma structures, are the same ones that walk a razor-thin line between holding together and flying apart. Think about what's actually happening here from a physics standpoint. You've got a nucleus that's maybe a few kilometers across, made of materials that have been frozen solid for potentially billions of years. This object has been drifting through the cold void of interstellar space at temperatures barely above absolute zero. Then suddenly, it plunges into the inner solar system, where temperatures spike dramatically. The thermal shock alone is enormous. The outer layers heat up and start sublimating within days or weeks. But that heat doesn't stop at the surface. It conducts inward slowly, raising the temperature of deeper and deeper layers. The problem is that this process isn't uniform. Different materials conduct heat at different rates. Cracks and voids in the structure create insulated pockets where heat builds up faster than surrounding areas. What you end up with is this chaotic patchwork of temperature gradients throughout. The sudden decompression can be violent. Material that's been locked away for eons comes blasting out through whatever path it can find, whether that's an existing crack or by creating a brand new fracture. That's why we're seeing these discrete pulses of activity, rather than a smooth, continuous fade. Each pulse represents another pocket deep in the nucleus, finally reaching its breaking point and venting to space. Now, here's where it gets really interesting. From a structural mechanics perspective, every time one of these jets fires, especially if it's firing from an off-center location, it creates an imbalance. The nucleus is spinning, and now you've got this powerful jet of material shooting off to one side. That's going to create torque, which changes the rotation rate. But it doesn't just change how fast the nucleus is spinning, it can also change which axis it's spinning around. If enough jets fire from different locations over time, you can end up with what's called a tumbling rotation state, where the nucleus isn't spinning smoothly around one axis anymore, but wobbling chaotically. That kind of complex rotation puts enormous stress on the internal structure. Parts of the nucleus are being pulled in different directions by centrifugal forces that keep changing magnitude and direction. If there are already weaknesses in the structure, pre-existing cracks or boundaries between different types of material, those become failure points. This is exactly how comets break apart, not usually from one catastrophic explosion, but from accumulated damage over time. Each outburst weakens the structure a little more. Each change in rotation stress tests the nucleus in a new way. Eventually, something gives. Right now, 3I Atlas is still officially one single nucleus. There's no confirmed secondary fragment, no obvious chain of debris stretching out behind it in its wake. But the signs of stress are absolutely there. The changing rotation period tells you the torque balance is shifting. The persistent activity this late in the outbound journey tells you there's still plenty of volatile material deep inside that hasn't vented yet. The evolving coma structure tells you the venting pattern is changing as new jets turn on and old ones potentially shut down. All of those are warning signs that the nucleus is under significant mechanical stress. Now, does that mean it's definitely going to break apart? Not necessarily. Some comets hold together through far more dramatic activity than what we're seeing here. The structural strength depends entirely on how the nucleus is put together internally, and we have almost no direct information about that. What we can say is that every additional day of fresh activity increases the cumulative stress on whatever is holding this thing together. And that brings us to the question everyone's asking: what happens next? There are really several possible scenarios from here, and which one plays out depends entirely on what's happening deep inside that nucleus right now. Scenario 1. This is actually the tail end of the thermal wave. The heat front has penetrated almost all the way through the nucleus, triggering the last remaining pockets of volatile material. Over the next few weeks, we'll see activity taper off dramatically as those final reserves get exhausted. The brightness will finally start dropping the way models predict. The rotation will stabilize. The non-gravitational forces will fade to near zero. 3I Atlas will coast back out into interstellar space as a relatively inert, processed chunk of rock and depleted ice. That's the optimistic scenario, where the comet survives intact but finally quiets down. Scenario 2, there's still a substantial reservoir of volatile material deep in the core that the heat wave hasn't fully reached yet. What we're seeing now isn't the end, but actually a middle phase. As that heat continues to penetrate deeper, we could see activity levels stay elevated or even increase again before finally dropping off. This scenario extends the active phase significantly, potentially by weeks or even months. The longer the activity continues, the more cumulative stress builds up, which increases the chances of structural failure. Scenario 3, the accumulated damage from weeks of outgassing and changing rotation has already compromised the structural integrity to the point where the nucleus is on the verge of breaking apart. The fresh activity we're seeing today could be coming from jets that are actively exploiting or widening existing cracks. In this scenario, we might see the appearance of fragments within days or weeks. It might not be a dramatic explosion, but rather a slow disintegration where pieces gradually drift apart. Scenario 4, and this is the most dramatic possibility, one of those deep volatile pockets is substantially larger than average, or multiple pockets are clustered in one region. When they eventually vent, the outburst could be powerful enough to catastrophically disrupt the entire nucleus. We'd see a sudden spike in brightness, followed by the emergence of multiple distinct fragments, possibly with their own individual tails as each outgas independently. Which scenario plays out depends on factors we simply can't measure from Earth. We can't X-ray the nucleus to see its internal structure. We can't map the distribution of volatile ices deep inside. We can't measure the strength of the materials holding it together or see where the cracks and weak points are. All we can do is keep watching, keep measuring, and let the comet tell its story through its behavior. That's why today's observations are so significant. They're telling us that the story isn't over. Whatever's happening inside 3I Atlas, it's still actively unfolding. The comet is still in the middle of processing the energy from its solar encounter, and we're watching that process play out in real time through these persistent changes in brightness, structure, and motion. For anyone who studies comets, this is absolutely fascinating. Interstellar comets are rare enough that every single observation adds to our understanding of how these objects behave. The fact that 3I Atlas is staying active this long, this far from the Sun, tells us something important about either its composition or its internal structure, or both. Maybe interstellar comets retain volatiles deeper and in larger quantities than comets native to our solar system. Maybe the extreme cold of interstellar space creates a different internal structure that responds to solar heating in unexpected ways. Maybe we're seeing evidence of compositional differences that reflect the different conditions in whatever stellar system 3I Atlas originally formed in. Every additional observation, every unexpected behavior, every deviation from predicted models gives us another clue about what makes these interstellar visitors unique. So if the next round of observations finally shows the brightness curve bending downward hard, if those expanding shells start fading, if that extra bump in the light curve begins to shrink, and if that persistent thrust in the orbital drops towards zero, then today's fresh activity is one of the last gasps before a real permanent fade-out begins. But instead, if the observation logs keep saying the same thing over and over, if new structures keep appearing in the coma, if the spin keeps getting updated, if that persistent thrust keeps showing up in the orbital calculations, then we're not watching a cool-down phase at all. We're watching an interstellar object stay alive and active far longer and under far more internal stress than anyone thought possible when this thing first showed up in our solar system. The next few weeks are going to be critical. Every observation session adds another data point to the story. Every image shows whether new structures are appearing or old ones are fading. Every brightness measurement shows whether the curve is finally dropping or stubbornly holding steady. And through it all, 3I Atlas just keeps going, keeps surprising us, keeps defying expectations about how a comet should behave this far into its outbound journey. So, if you want to find out whether this interstellar visitor finally runs out of surprises, or whether this situation escalates from concerning to critical, stay tuned. This story is